Did you know that our universe supposedly originated from a singularity? We usually only find this mysterious unit of physics in the center of black holes. But what if these singularities don't exist? A scientist has now shown that the idea of a singularity may be a mistake, and that would mean that our universe may not have started with a Big Bang. A singularity is theoretically a point at which something is infinitely small and infinitely dense at the same time. This phenomenon is probably found in the center of black holes, where gravity is so strong that nothing can escape, not even light. At this point, the known laws of physics stop working. Theoretically, such a singularity also existed at the beginning of the universe when all matter and energy were concentrated in an infinitely small point. But here's the kicker. What if these singularities don't exist? Roy Kerr, a well-known physicist who, among other things, discovered the Kerr metric, doubts the idea, and with good reason. Kerr is a specialist in black holes and was the first to describe the gravitational field of rotating black holes. Where does the idea of singularities come from? Have you ever wondered how scientists come up with these ideas? The Big Bang, the inside of black holes, and much more? It's well known that nothing and nobody can enter a black hole, nor did any of us witness the beginning of the universe. So how do scientists know this? The idea of the singularity arose from Albert Einstein's general theory of relativity. In the theory, which was published in 1915, Einstein describes how masses bend space-time and thus create gravity. One of the earliest solutions to Einstein's field equations is the Schwarzschild solution, which describes the gravitational field of a non-rotating, spherical mass object. Carl Schwarzschild discovered that such a body could have an event horizon, a boundary beyond which nothing, not even light, can escape. At the center of this solution lies a singularity, a point of infinite density and gravity where the known laws of physics break down. Schwarzschild thus described a black hole in the 1920s without knowing that these objects even existed. The singularity was therefore derived purely mathematically and was there before the objects were discovered that come very close to this description. However, we may have made a mistake here, and black holes are actually something completely different. Roger Penrose proved mathematically in 1965 that singularities are inevitable in general relativity if an event horizon exists. This means that black holes must inevitably contain singularities if they have an event horizon. We can see the event horizon of a black hole differently from the interior. The scientists thus combined a visible phenomenon with a mathematical conclusion. The event horizon is the boundary beyond which matter is so close to the black hole that no known force could pull it away from there. However, there is a small catch with this idea. Stephen Hawking proved that there is a small amount of radiation coming out of black holes. This means that the event horizon is not absolute. Roger Penrose was awarded the Nobel Prize in 2020 for a paper that again dealt with the singularity. He showed that space-time is so strongly curved in the vicinity of a singularity that the laws of physics as we know them are no longer applicable. Penrose's singularity theorem is based on the concept of geodesic incompleteness, which states that the paths of particles and light rays, referred to here as geodesics, must end in a black hole. This suggests that space-time itself ends at these points, leading to the idea that singularities are real. The importance of this theory should not be underestimated because it highlights a fundamental contradiction between general relativity and quantum mechanics. While general relativity predicts singularities that are points of infinite density and gravity, quantum mechanics breaks down at these scales because it does not allow for such infinities. This contradiction shows us again that somewhere in our physical disciplines, we have a flaw that we have not yet found. We cannot separate general relativity and quantum physics. They both describe our world. If singularities do not exist, as Roy Kerr's latest work suggests, the consequences could be profound. Kerr impressively shows that Penrose's conclusions may be wrong and that rotating black holes do not have point singularities but rather a ring-like structure, or no real singularity at all. This realization could mean that space-time does not end inside black holes. If K's ideas are correct, this would mean that the general theory of relativity also works without the need for singularities. This could eliminate the contradiction with quantum mechanics and add completely new dimensions to our physics. What does the Kerr metric say? It's incredible how much these mysterious black phenomena challenge our scientists these days. Black holes are once again being touted as the key to a comprehensive understanding of the universe. After all, they are among the most mysterious objects in the universe, and they probably combine incredible powers. The Kerr metric was developed in 1963 to continue the Schwarzschild solution. Schwarzschild dealt mathematically with non-rotating, spherical black holes, and Kerr devoted himself to rotating black holes. This is quite a difference. Most astrophysically known black holes rotate, but not all of them, and they do not all have the same shape. In his work, Kerr described a black hole with two horizons, the outer event horizon and the inner Cauchy horizon, as well as a ring-shaped singularity. These rotating black holes also have a so-called ergosphere, in which space and time are entrained by the rotation of the black hole. The ergosphere is an area outside the outer event horizon of a Kerr black hole in which objects are forced to rotate with the black hole. Within the ergosphere, it is theoretically possible to extract energy from the black hole. The Kerr metric shows us that the behavior and structure of black holes can also be described and evaluated differently than the researcher Schwarzschild did. The metric has been used since the 1960s to understand the dynamics of accretion disks, jet formations, and other high-energy phenomena surrounding black holes. K's discoveries have had a significant impact on theoretical physics and astrophysics, and have also changed our understanding of gravity. Now, Kerr has proposed further theories that question the existence of singularities and potentially offer a new perspective on the structure of black holes. Roy K's discoveries and theories have greatly expanded the understanding of general relativity and the structure of the universe, particularly in relation to rotating black holes and the complex phenomena that surround them. In his work, Kerr argues in a very comprehensible and mathematically correct way that the assumption of singularities in general relativity is possibly wrong. He explains that the mathematical calculations that point to singularities do not necessarily mean that such points must exist in the real world. The values used in these calculations do not necessarily indicate actual physical endpoints. What does quantum gravity tell us? We are once again faced with a scientific puzzle. Even if there are no singularities and a scientist can logically show that the assumptions of general relativity do not have to exist in reality for our physics to work, what else is real? How do we unravel the mysteries of the universe? And can we ever find out what the truth is? We are probably at the point where our research and observations are forcing us to finally find the unification of the quantum level with the world of physically observable objects. Einstein called this the unified field equation, a formula that describes the microcosm and macrocosm in equal measure. This formula must exist, or perhaps said a little better, there must be a bridge between the two. We don't know whether we will ever really be able to physically and mathematically grasp everything that the universe really is. Imagine if a physicist wanted to calculate your body. You could use certain measures of length and width, perhaps describe gravitational processes, your weight, the circulation of your breath, or how you accelerate when you run. But it's clear that physics will never be sufficient to describe such a complex but also completely natural object as your body. It could be similar with the universe. Perhaps we have only seen, measured, and calculated this one side for far too long. However, we have overlooked the fact that the universe has dimensions that elude this scientific discipline. The original problem stems from the fact that people have long thought that stars, planets, and everything we see in the universe are simply dead objects. For around 100 years, we have known how dynamic the universe really is, and now we are on the threshold where we have to adapt when it comes to predictability. The quantum world, in particular, teaches us that nothing is as it seems. Quanta are the building blocks of the world we see, and they are not static, not predictable, and not even really solid matter. Roy Kerr is one of the proponents of loop quantum gravity, which describes spacetime as a network of small, separate building blocks. This is similar to string theory, which postulates fundamental building blocks of the universe as one-dimensional threads. Both theories can theoretically bring the subatomic and visible worlds together. General relativity describes gravity and the structure of the universe on large scales, such as planets, stars, and galaxies. Quantum gravity attempts to describe gravity as a quantized interaction, similar to the other fundamental forces. In loop quantum gravity, gravity is caused by the small units, and in string theory, gravity is caused by the oscillations of the threads or strings. In these theories, the force itself, which we know as gravity, originates from a particle that scientists call a graviton. However, the graviton has not yet been found or proven. Work on this is being carried out at the Large Hadron Collider in Geneva, among other places. So far, despite the possible solutions, we only have theories and assumptions but no real explanations or evidence. In 2024, scientists discovered that quanta behave very differently than previously assumed. They can change their behavior very quickly under certain conditions. This means that they exhibit movements and dynamics that are far removed from our familiar Newtonian laws of motion or gravity. Wherever we look in physics at the moment, whether at the temporal edge of the universe, whether JWST is discovering one impossibility after another, at the smallest particles, or even in theoretical physics, the old values are crumbling everywhere, and completely new and unexpected worlds are opening up. Become a subscriber now. The best and most exciting videos are yet to come.